Okay, we're still in 1.2 graphs and lines in Barnett, and we will now pay attention to the next goal of ours, which would be being able to calculate the slope of a line and graphing special forms of equations of lines. That being said, why don't we take a look at some of these special cases. The graph of x equals k is just the graph of a vertical line k units from the y-axis, whereas the graph of y equals to k is the graph of the horizontal line k units from the x-axis. To see some examples here, consider graphing these two lines. X equals to -7 and y equals to 3. Well, x equals to -7 could really be interpreted as every single point on my vertical line has x coordinate of -7. So if I were to quickly draw an x and y axis, where should I draw the line so that every x coordinate of the line, and it's a vertical line as we already know, has a value -7? Well, here's the origin. Count 7 units to the left and then draw our line there. This vertical line, x equal to -7, represents all the points in the plane whose x coordinate are -7. Likewise, the horizontal line y equals to 3 is the line that's 3 units from the x-axis, so go up 3 units, draw a horizontal line. We can make this probably a little nicer here. And all the points on this line have y coordinate 3. So for example, the y-intercept would be 0, 3. The x-intercept would here for this line would be -7, 0. Here is the solution for x equal -7, and we actually graphed y equals to 4 instead on this page. So once again, x equals to -7, 7 units to the left of the origin, vertical line, y equals to 4, horizontal line 4 units up, because this is positive, from the origin. Okay, moving on to the slope of a line, a topic that everyone probably remembers, but the slope of a line is given by this formula, y2 minus y1 over x2 minus x1, where x1, y1, and x2, y2 are just 2 points on our line, and what really this represents is the rise over the run ratio. In other words, the vertical change, the rise is called the vertical change, denoted delta y, vertical change, divided by the horizontal change, which is given by the run. This delta x, delta is the Greek letter that stands for change, delta x, the change in x, or the horizontal change, also known as the run. Okay, so as you all know, the slope gives us an idea of steepness, how steep a line is. Quite widely applied in all of mathematics now and later if you do more math. So that gives rise to the equation y equals mx plus b, which is called the slope-intercept form because it has m as its slope and b as its y-intercept. Something that all of you have seen before, I'm sure. So why don't we practice here? Here's an example. Find the slope and y-intercept of the line whose equation is 5x minus 2y equals to 10. This equation is in what form? Well, if you're thinking standard form to yourself, you're correct. Our goal would be to first change this equation into slope-intercept form. Once we've done that, we could very easily identify what the slope and the y-intercept are. Okay? How do we do this? We isolate y by itself on one side and move everything else to the other side. In other words, we solve this equation for y. Okay, so how about we add, or rather subtract, 5x from both sides, and then divide both sides by -2. And doing so will give us y equals 5/2 x minus 5. This is now in slope-intercept form, and we could easily identify the slope to be 5/2 and the y-intercept to be -5. So really the coordinates for the y-intercept are 0, -5, and the slope is 5/2. Another form of an equation of a line that you might have heard of is the point-slope form, which is written here as y minus y1 equals m times the quantity x minus x1, where m is the slope and x1, y1 is just a given point on the line. Okay, so with that being said, you might wonder, well, this looks familiar, and yes, it does, because this is really derived from the definition of slope, y2 minus y1 over x2 minus x1. We just sort of took the denominator and multiplied by it on both sides, and we substituted the more general value of x for x2, since we only know one point on the given line. Okay, so here's an example that we could practice on, and you'll have to work on your homework. Find the equation of the line through the points negative 5, 7 and 4, 16. First of all, every time you're asked in this class to find the equation of the line, that means that your final answer should always be in slope-intercept form. Always, always, always. That being said, we're given 2 points that the line goes through. The easiest thing to do is to calculate the slope first. So let's calculate our slope. And if you remember, we have a choice which one to call x1, y1 and which one to call x2, y2. It's really up to us. I'll call this point x1, y1, this one x2, y2. So the slope is y2 minus y1 over x2 minus x1. Vertical change over horizontal change. That gives me 16 minus 7 over 4 minus negative 5. Well, 16 minus 7 is 9. 4 minus negative 9 is also 9. I get a slope of 1. Okay, so I know that my line would look something like y equals x plus b. The slope is 1. Well, to find b, what could I do here? I could either use point-slope form, or I could just use one of these 2 points and plug in for y and x to find b. So why don't we use point-slope form to get the equation. I'll put to get b in the rest of the equation, essentially, right? So point-slope form is y minus y1 equals m times x minus x1. We know that our slope is 1. What we're going to do here is we're going to replace x1, y1 by one of our 2 points. And I'm going to use the second point. So y1 will be 16, x1 would be 4. Okay? And now we turn this into slope-intercept form. Adding 16 to both sides gives us x plus 12. And that's the equation in slope-intercept form. We found the equation of this line.